Hi, welcome to this tutorial on chemical equilibria and the Chatelier's principle. In the previous tutorial, we learnt about Maxwell-Boltzmann distributions and about how catalysts affect them and also temperature. So in this topic, it's a slightly new topic, slightly new way of thinking. We are looking at what reversible reactions are and applying the Chatelier's principle. So key terms we're going to come across: reversible reaction, dynamic equilibrium, and closed systems. So those are three things we really need to understand in order to master this topic. So you're going to see this a lot. This is a reversible reaction sign. So it means the reaction can occur in both directions. Okay, so this half-headed arrow above a half-headed arrow. So the reactants can form products and the products can also form reactants. And the direction in which the equation or reaction goes depends on the conditions of the system. So the forward reaction, it's a change from the left to the right. So if we're favouring the forward, and then we've got the backwards reaction is a change from right to left. Okay, so the double-headed arrow shows that reversibility. We need to understand what a dynamic equilibrium is. So when the forward reaction is happening at the same rate as the backwards reaction, so the concentration of both the reactants and the products remain constant. That does not mean the amount of them is the same. So an analogy I often use is I say, imagine I've got 20 students on one side of my room and I've got 5 students on the other. So 20 on one side, 5 on the other. And I ask one student from each side to cross over. How many do we now have? We've still got 20 on one side and 5 on the other. I now ask 2 people to swap over. So the forward and backwards rate is the same. If they both cross over from both sides, I've got 20 on one side and 5 on the other. So the amounts are remaining constant, but they're not the same necessarily. I've actually got a difference in the amount. I've got 20 on one side and only 5 on the other, but it's constant. The forward and backwards reaction are happening at constant rate. I also like to consider analogies to do with escalators. So if you've ever been really silly and gone on the wrong side of an escalator, so imagine if the escalator is going down at the station and you're walking up it, hopefully you appreciate that if you walk up the escalator and you keep walking at exactly the same rate as the escalator is traveling down, you're going to hold your position. You're not going to move. You're going to stay still. You're still moving though. The forward reaction is still happening. The backwards reaction is still happening. There's still movement going on, but you're cancelling it out and you're staying in the middle. Okay, so the forward and backwards rate of reaction is happening and it remains constant, but you're not going to move anywhere unless you change the conditions, unless someone pushes you up or pushes you down. Okay, so think about the classroom analogy, think about the escalator analogy, whatever it is you need. Analogies really help with this topic. It can be quite difficult to get your head around sometimes. So we've got 2 graphs here as well. We've got rate over time. So if I start with a container that's got loads of reactants and no products, I'm going to obviously start using my reactants up. So I'm going to have a forward rate that's going to be really high because I've got loads of my reactants and no products. If I make a pretend reaction here, I've got A on this side and B on this. If I have a container just with A in it, I'm going to have loads of A at the start, and we're going to be the forward reaction is going to be happening a lot because I need to make some B, and I'm going to have no rate of reverse because I don't have any B to go backwards with. But as the reaction proceeds, you can see the forward rate starts to slow down, the reverse rate starts to pick up because as I start making B, I can start doing the reverse reaction. And eventually we're going to end up with both the forwards and backwards rates happening at the same time, and that's the point at which you on the escalator have found your point where you're walking up at the same rate as it's going down. And then over here, this is a different thing. This is amount over time. So this fits with, again, I've got A and B, and at the start, I'm not going to have any B. There's no products in my pot at the start, is there? I haven't made any yet. And I've got all of A. So the A is going to start getting used up and turning into B, and that's where we get this swapping over. And eventually we're going to reach what we call equilibrium, which means that although the forwards and backwards reactions are happening, the amount of A and the amount of B that I have remains constant. And that is like in my classroom, I've got 20 on the left or the right-hand side on one side of the classroom and 5 on the other side of the classroom. Eventually my system will reach equilibrium where it will just continuously be 20 and 5. There is movement, people are crossing over, but overall I've got 20 and 5. That doesn't change. And that is what that represents, that equilibrium. Now that will change if I suddenly set a fire off in the classroom, for example. That might start changing the numbers. So if I change the conditions, I may well push the equilibrium, I'll move it around. Okay, so this is all enclosed systems that we're considering this. We're not adding any more people to the classroom, you know, in my analogy. So the equilibrium, at equilibrium, the quantities of everything present, so the concentration of the reactants and the products in the mixture remain constant, although the reaction is still continuing. And this can be a little bit misleading to look at because this has actually got the same number on both sides. Remember I said that you don't need to have that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so if I added just a few more of A, okay, so this can still be at equilibrium, right? I can have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9 on this side and 1, 2, 3, 4, 5 on this side. At equilibrium, the amounts will remain constant, but the forward and back is still happening. So at any one time, if I checked, I'd still have 9A and I'd still have 5Bs. But they are, occasionally one will swap over to the side and they'll each do it at the same time, as you can imagine, or 2 will swap over, or 3 will swap over. But overall, the amounts are the same. So a dynamic equilibrium only occurs when you have a reversible reaction in a closed system. Like I said, we're not adding extra people in or molecules in. It's a closed system, and that's what this box is going to represent. So nothing can be added or removed from the system apart from, well, energy. Yep. So on the left diagram, we've got lots of A. This is the start of the experiment, and it's going to start being converted into B. On the right diagram, after a while, it's eventually going to reach what we call dynamic equilibrium. We're going to see no further change. And you can see there isn't the same numbers. There's 1, 2, 3, 4, 5, 6 on this side and 4 on the other, but that's going to remain constant. There is constantly going to be 4 A's and there's constantly going to be 6 B's. Okay, even though there is movement going on. So on the escalator, you're still going up, the escalator's still going down, you're going to hold that position. You're not moving anywhere. If it was an open system, we wouldn't be able to show this very easily. Okay, so we'd have lots of A, it's going to be converted to B, and if we start losing the B, then it's going to mess up with our equilibrium, isn't it? So B is going to be lost, but no A is remade. So eventually we're going to end up losing our atoms, and it's not possible to really show that. We can apply something called Chatelier's principles to dynamic equilibrium. So if a dynamic equilibrium is disturbed, so you've allowed it to reach equilibrium, we've got the 9 on one side, 5 on the other, they're perfectly happy, they're forward-back reactions happening, but they're constant amounts on both sides. We can disturb that by adding heat, removing heat, adding some more molecules in, so changing the concentrations. And to explain what happens, we use Le Chatelier's principle. So if I write the equation, these two things, reacting A plus B is in a reversible reaction with C plus D. The position of equilibrium is going to move to counteract that change. And I liken that to the person on the escalator is going to move their position on the escalator, for example. So yeah, you can change the temperature, the pressure, the concentration. So more reactants will be produced if the equilibrium moves to the left. So if we shift in this direction, we're going to get more of this. If the equilibrium shifts to the right, we're going to get more of our products. And that's helpful for industry. As I said, these are the factors that are going to affect the position of equilibrium. So concentration, pressure, temperature, and not a catalyst. Okay, a catalyst is not going to affect the position, but it will affect the speed at which you reach equilibrium. So here is an increase in the reactants. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's going to, I've got A plus B is going to be reacting together to make C and D. The equilibrium is going to shift to the right and more A is converted to B and vice versa. I mean, it doesn't really fit with this diagram here. So why don't we just think in terms of, if you look at this image down here instead, if I increase the amounts of A and B, the equilibrium, according to Le Chatelier's principle, we're going to want to counteract that change. We're going to want to reduce the amount of A and B. We're going to want to use A and B up. So we're going to shift the equilibrium to the right. And we used to say it's going to favour the forward reaction, but that's gone out of fashion. We're going to shift the equilibrium to the right using the word shift. And we're going to try and use up some of that excess A and B that we've just added in. Okay, so that's what we say. It's going to shift to the right and more A and B is converted into C and D. Now, the opposite is going to happen if we add in more C and D. If we add in more of this, if this increases, we're going to shift the equilibrium backwards or to the left, and that's going to try and use it up to counteract the change. That is Le Chatelier's principle. So I've summarized it here. If you increase the reactant, we're going to shift to the right. This is going to lead to more products being formed, so more of the extra molecules are used up. If we increase the concentration of the product, we're going to shift to the left instead, and we're going to end up with more of the reactant being formed, okay? When we're considering changes in pressure and the Chateliers, we need to think about the moles of gaseous molecules. So if we're looking at a really simple system here, we've got A on one side and B on the other. I've got 1, 2, 3 moles of A, or molecules of A, moles of A, and I've got 1, 2, 3, 4 of B. So I've got 3 and I've got 4. If I increase the pressure on the system, it's going to increase the pressure on both sides, and we're going to want to decrease the pressure of the system. So we're going to shift in the direction of less moles. Okay, so again, if I've got my two diagrams, so on this side, if I increase the pressure, we are going to shift this way, as my big arrow is showing, because we're going to want to favour the side of the reaction that's got the less moles of gas, less pressure. So if you increase the pressure of the system, it's going to increase the pressure on both sides. So we're going to shift the equilibrium to favour the side that's got the less moles of gas, and it's vice versa on the other side. So if you decrease the pressure, we've got 3 moles of gas on that side, 4 moles of gas on that side. We're going to shift to the side that's got the more moles of gas to get that pressure back up. The Chatelier is always wanting to counteract the change. So if you decrease the pressure, you're going to want to increase it again. So we're going to shift to the side that's got the more moles of gas. Okay, so here we've got an explanation. So increase of pressure, we're going to shift to the side with the fewest moles to counteract the change. If we decrease the pressure, we're going to shift to the side with the most moles to counteract the change. A good example with an actual specific example is here. We can see we've got 2 moles of gas on the right hand side. We've got only 1 mole of gas on the left hand side. Okay, so what do you think is going to happen if I increase the pressure on this closed system? If I increase the pressure on a closed system, the Chatelier's principle tells me I'm going to want to counteract the change. I'm going to want to decrease the pressure in the system. So I'm going to shift my equilibrium to the side that's got the fewer moles of gas. So I'm going to shift to the left. If I increase the pressure, I'm going to shift to the left. Okay, and vice versa. If I decrease the pressure, I'm going to want to counteract the change by increasing it. So I'm going to shift to the right, to the side that's got the most moles of gas. What about temperature? So this is where we need to know information about exothermic or endothermic. We need to know whether the forward reaction is endo or exo. So in this example, the forward reaction is exothermic. So all the arrows pointing to the right are exothermic. So the Chatelier's principle, if I increase the temperature, I'm going to want to counteract the change. I'm going to want to decrease it. So if the forward reaction is exothermic, and I increase the temperature, I'm going to want to cool the system down. So I'm going to take the cooler pathway, the endothermic. So I'm going to shift to the endothermic route, which in this case is the left. Okay. If I decrease the temperature, I'm going to want to warm the system up again. So I'm going to shift the position of equilibrium in the exothermic direction. And in this case, that is the forward or to the right. So again, we're just counteracting the change. So again, you can see it here. If I increase the temperature, I'm going to shift to the endothermic. Think of endo being cold. And if I decrease the temperature, I'm going to want to warm the system up. So I'm going to shift to the exothermic reaction. So first thing you need to know is your forward reaction exo or endo? Then go from there. Let's have an example. So if I've got calcium oxide, that is a solid, reacting with water, of course, liquid, I'm going to make calcium hydroxide, and that is aqueous. Okay, so this is quicklime and this is slaked lime. That's often what we call it. I've been told, this is really important, that the forward reaction is exothermic because there's a negative value here. So this is exothermic. Okay, so this forward is exo and the backwards is therefore endo. So if I increase the temperature on this system, the Chatelier's principle tells me I'm going to want to counteract that and decrease it, cool the system down. So I'm going to favour the endothermic. I'm going to shift it to the left. If I decrease the temperature, I'm going to want to warm the system up again. I'm going to warm it up and I'm going to take the exo. So I'm going to shift the equilibrium in the forward direction or to the right, the exothermic direction. Adding a catalyst is going to have no effect on the position of the equilibrium. If anything, it's just going to speed up the rate at which the reaction reaches equilibrium, okay? It speeds up the forward and back reaction by the same amount. So it's just like increasing the rate at which you walk up the escalator and the rate at which the escalator is traveling down. It's not going to move your position. So adding a catalyst, yes, will increase the rate at which you reach dynamic equilibrium, which can be helpful for industry. And we're not going to affect the yield of the reaction either, but it is helpful because it can provide alternative pathways, which can mean that we use less fossil fuels, and it's more sustainable for the environment. And it costs less as well. So catalysts are still very helpful, but they're not going to increase the yield and they're not going to change the position. So as you can see, this is a good diagram of the presence of a catalyst. This is without and this is with. I've increased my arrows, but of both the forward and the backward. So we're not going to go anywhere with that.